Hello again, folks, in 114. Today we're going to be covering the last section of Chapter 8.4. Here's the calendar. Today is Thursday, June 17th, so 8.4 is appropriate. Okay. The packet that I have for you today looks like this. Consists of this page, which is an overview. To help distinguish one term from another. I'll do this and I'll explain it. Let's see. The formula sheet I swiped from the textbook is very nice. They give you examples and how to read them, the dimensions of each shape. There's another formula here, Euler's Polyhedron formula. Okay. And then this is, I also included this because these are better drawings than the ones that I did in PowerPoint. Of 3D shapes, Platonic solids, Polyhedra in general, prisms, and pyramids. Okay. And then there's the actual examples, okay? So we will go through this. Let's get started. Always takes 2 clicks. Alright, there we go. Just my message. I answer that later. Okay. Okay, let's start with this. Well, you know what? Yesterday, I had given you actually this sheet. So let me just point out it just again real quickly. We have to deal with measurements in 3 dimensions now. We had discussed measurements in 1 dimension and in 2 dimensions, but the 3-dimensional objects that we are dealing with will have volumes, first of all, which is a measure of the capacity of basically the inside points in a space, like inside the container. If we deal with surface area, we'll be dealing still with 3-dimensional objects, but the measurement itself will be a 2-dimensional measurement because it's just a sum of areas. All right, so to illustrate that, although I didn't do a best job here, I gotta fix that. The surface area is basically the area on points, points on the object. So the area of this top, bottom, these 2 sides, the front and the back. And since they're all areas, again, I would classify that as a 2-dimensional measurement. Right? Still dealing with a 3D object, but more or less translating to a 2-dimensional measurement. Okay? So that's where we're at. Volumes and surface areas today. Let's see, what else? What is relevant now is this. Do this web here. Okay. We're dealing with what is collectively, very generally, referred to as either 3D objects or just simply space figures. Right? Now, there's lots of things that qualify as space figures. Right? Spheres are a space figure. That almost seems very appropriate, right? Because when you think of outer space, you think of literal outer space, I should say, when you think of the word space, you think of, out off the planet, and basically the shapes of the planets are spherical, even if they, in some cases, are flatter on top and below. Anyhow, a sphere is a space figure. A cylinder is a space figure. A cone is a space figure. But then there is this other category, polyhedra. Right? Now, just to loosely connect these three things together, I describe them this way: spaces enclosed by curved surfaces. So the sphere being the ultimate, right? It's a curved surface all the way around. Right? A cylinder is curved in basically this orientation, sort of vertically here, enclosing in that respect. But then it has an edge basically all the way around it. Circles don't have edges really. Cones also are, enclosing via a surface, right? Bending a surface in 360 degrees generally. All right, if we're talking about a circle as a base. All right, the polyhedra, which is the meat of this section, are defined as spaces enclosed by the union of polygonal, or you could say polygonal regions, right? Polygonal surfaces. Regions and surfaces are just interchangeable terms, all right, at least in the context I am using them, all right? And there are three subcategories here. Right? There may be some overlap, if you consider an individual example, but here are the three basic subcategories of polyhedra. Right? Polyhedra is the pluralization of polyhedron. All right. There are what are regarded as the 5 Platonic solids, and these are things that they have some very consistent, uniform sort of shape that from which they are comprised. Now, I just use this as rather than a circle, which is what I usually use in my diagrams. I gave you an actual example of a Platonic regular polyhedra. All right, a cube. Right. Well, what I hope to imply is a cube. What qualifies as a regular polyhedra, aka a Platonic solid? All of the surfaces, which are called faces, all right, are the same size and shape. They're truly congruent. Let me add a little notation here because that is important. All right. Remember when, from the parlances of previous sections here, when you have a shape that is the same size and shape, right? Another way of saying that is congruent. Right? Okay. But what is very important to add some distinction from this and this is that they are regular polygons, right? Which means that they are, if you were to examine the sides, they'd all be the same side. If you were to examine the angles, the interior angles, they'd all be the same angle, right? That means, just to add to this as well, they're equilateral and equiangular. All right, that is important. In order to qualify as a regular polygon and therefore as a regular polyhedra, the parts from which a polyhedra are made are polygons. If it's truly regular, then it has to meet these qualifications, okay? Now, if you're a prism instead, all right, they changed the word slightly. You could regard these in a very general way as being faces as well, but if two of them happen to be identical, and then the things that are connecting them are usually, they don't have to be rectangles per se, they could just be parallelograms in general. If they're four-sided shapes here, just connecting between them, this is referred to as a prism, right? So to make it easier to kind of distinguish one in your own mind, I try to be consistent in how I describe these. So regular polyhedra, all faces are the same size and shape, regular polygon. When you're talking about prisms, there are two bases, all right, that are the same. All right, now just to kind of illustrate here. This is a base, even though it's not sitting on itself. and this down here is a base. Because they are the two faces that are the same essentially, and everything else is different. They're general polygons, which means that they're enclosed multi-sided shapes in 2 dimensions, but they don't have to be regular, right? Right. This dimension could be a little bit longer than the dimension connecting here and here, right? The length here and here. All right, so general polygon. The polygon bases, the only two that are the same, are connected by lateral faces. That's the name of these things that are all side by side, right? Are parallelograms, to be more general, right? Now, they look like rectangles, quite frankly. I wanted them to, right? But they don't have to be rectangles, right? They usually are, right? If they happen to be rectangles, I don't know if that's in the frame here. It's a little hard to see. I'll just highlight this. If rectangles are used specifically, then it is referred to as a right prism of some sort. Right, similar to a right cylinder. Okay. Then there's this category, the pyramids. Right. Again, to add some sort of symmetry here. All faces to be very general, 2 bases to be a little bit more specific, and then there's the situation where you have a pyramid where you have only 1 base. Right. So that would be referring to the bottom part of this upon which the pyramid rests. Right. The lateral faces are pitched inward. They form a point. All right. This is a vertex, right, where the lateral faces intersect. Okay. Now, bearing that in mind, let's look at this example from the examples from this other sheet. All right, regular polyhedra, prisms, and pyramids. All right. As I said, there can be some overlap. All right, but those are the general ideas. All right. Here at the very tippy top are 3-dimensional solid objects. That's the ultimate in generalization for this section. All right. A rectangular solid in this case, what appears to be a cylinder, a cone, and what appears to be a sphere. All right. Being very general, you can refer to these as solid 3-dimensional objects, or space figures, if you like, again. If you get a little bit more specific, again, here are the actual examples of the 5 Platonic solids. All right. Notice what is true about them. The most basic one is a tetrahedron. All right. It's a 4-faced space figure. All right. This face, this face, this face, and the face behind them. And they're all regular polygon triangles, right, which means that they're probably all equiangular, 60 degrees each, and the same side length. Right? And you can enclose the space using that same shape over and over again, and only that shape, right? In which case, again, you get a tetrahedron, right? More famously, and I use this as my own example, is a cube, right? It's a Rubik's Cube, right? Right. One cool thing about a Rubik's Cube is that they actually, of course, the sides are colored, right? So, you could see that although there are different sides, distinguished by color, they're all the same basic outline shape here. They're all one big square, if you will. All right. as you rotate, right? A cube has 6 faces and 8 vertices. That's the corners, of course, and the edges are what we would think of as a side in 2 dimensions, right? We call them edges when we talk about spaces. All right. Maybe make that distinction, right? What are referred to as sides of a polygon in 2D is an edge. When we're thinking about them, a polyhedron in 3D. Okay. Then there's the next one, an octahedron. An octahedron is also a Platonic solid, right? It looks like a pyramid butted up against another pyramid, but the faces are all the same triangular shape. Right? And then this is cool, a dodecahedron, which is made of pentagons enclosed. And I always mispronounce this. Icosahedron is a 20-faced, looks like Dungeons and Dragons style die. If a cube is, you know, a regular die, right? Then this would be something like a Dungeons and Dragons die, you know? Something like that. Icosahedron. Here we go again. If you're now taking a sphere and a cone out of the conversation, and you're limiting your scope to just the polyhedron, polyhedra to pluralize, then no sphere, no cone, no cylinder. All right. These would all classify as polyhedra in general. All right. This is not. This particular one, perhaps, if it's a cube, would be a regular, right? If this is a cube, then it's regular, right? Polyhedra. Platonic solid, right? Same thing here. If this particular tetrahedron here, if it's a tetrahedron, then it is also regular. Polyhedra, Platonic solid. This seems to be exaggerated a bit one way. So there is, although it is enclosed, and it is similar looking to the Platonic solids, that one of them that we just looked at, this is probably not regular, all right? And this appears more like a prism than anything else. It's just not specifying. If you get down here where you go, all right, let's consider this as, instead of the regular category, the prism category. Take a look at these. Here you have prisms. Why? Again, because you have 2 bases. A top base, as it is specified here, and the same shape as the bottom base. And what's connecting them, whether in the front or the back of the sides, are parallelogram sides. Faces in the context of 3D. Okay. Technically, even if this is a cube, all right, a cube would also qualify as a prism. As I said, there is some overlap between the categories. You know, you could draw a Venn diagram if you really wanted to. But if you're going to choose between referring to a cube as a prism or the alternative, a Platonic solid or regular polyhedron, since it qualifies more strictly, right, as this, that it's all the same shape all the way around, and I would go with that. You know, it isn't wrong to call it a prism though, because it technically is. Right? Here's a hexagonal base as a prism here. And notice again what the sides are. They're all parallelograms. Now perhaps they are rectangles, but even if you had something slanted, it would be okay, as long as it is the same shape in the base above and below. It's not a very good drawing, but if you can imagine this cropped slightly, at an angle, they would still be parallelograms, just not rectangles per se, and qualify as a prism. It's something that is a trapezoidal style prism. Down here you see pyramids, right? Here's that one from early, I believe, although you don't really have dimensions to really specify, right? But this is still a Platonic solid, if in fact, all of the sides are the congruent shape, and they appear to be. Same size and the same shape, so equiangular polygons and equilateral polygon. But they could also be classified as pyramids. Again, there is some overlap between those three categories, right? Just not entirely, I suppose. This is the Great Pyramids in the Great Pyramid, among other pyramids in Egypt, looks like this type of pyramid, a square base. Okay. But you're not limited to that. You could, in fact, have a different shape. This one has a hexagonal bottom, and this one looks like slanted. Pyramid. There's a name for that, I believe, and I hope you'll forgive me. Yangma, I believe that is pronounced. Oblique. It's slanted perhaps one way. At least if it had a truly a right angle side here, if that were the case, then it would be a slanted oblique or Yangma pyramid. It may not be that exaggerated, or it could be the angle that I'm looking at it, right? If it is slanted at 90 degrees, to the point that one side is 90 degrees. Okay, so this is still qualified as a pyramid. It has one base, right? The base but which one do you choose? It could be any of them in theory in that case, right? But it is also, perhaps it would be more appropriate to refer to it as a Platonic solid given the choices, right? But it still would qualify as a pyramid, okay? Now, these formulas are very useful. You know what, there was one other thing I'd like to point out if I could. Let me see really quickly if it's visible. If you look at this again, sorry, not to make it get dizzy here. If you look at this page just for a moment or longer, I like this because they took the time to actually draw. All right, remember, a corner is a vertex, a face is what you would think of as a side in 2 dimensions, but we're going to use a surface rather. A face is a surface. All right, a side is an edge in 3D. Right? All right, a 2-dimensional surface is a face, right? And a corner is always a corner. Right. When we get into Euler's Polyhedron formula, you need to be able to count and distinguish those. Right. All right. Let's see. Let me finally get over this. Here's that formula sheet, as I mentioned, I swiped from the textbook because it's very nice. There's lots of words to describe the same thing, but just to reiterate this point. Sides in 2D are called edges in 3D. A face could be called a base if two of them happen to be the same. But more importantly, a face, which again is normally what we have in 2D, in 3D, is a surface in 2D, right? And an alternative word is region. Okay. Now here's the formulas. If we calculate V for volume and SA for surface area, right? Taking advantage of the nature of the cube, right? You're probably more familiar with this incarnation of volume of a rectangular solid. Length times width times height just really crunched together. Length times width times height is just abbreviated without the dots even. If the faces are all the same polygon, congruent, above, below, all around it, and underneath it, then there's no reason to give it distinct labels, length, width, and height. You could just call them, surface. So S times S times S, abbreviated, would be S cubed, naturally. All right. If you're looking to calculate the surface area, one would need to calculate the surface area of just one example, and then multiply by 6. Right. In that instance, the edges, the sides, you need to know what that dimension is, and then square it. Right. It's the side dimension times itself, of course. A rectangular solid, it's a little bit more complicated because you have distinct measurements for the side edge dimensions. Okay, so it is still this idea of an area times an extra dimension. Remember, this much of it is an area, and times h gives it depth or height. But when you're trying to calculate the surface area, remember that you have two of each. You have the front face and the back face. You have the right side and the left side in theory. It's just not visible. You have the top in theory and the bottom. So that's why times 2 times 2 times 2. Do follow the order of operations, do the multiplications before you add. Okay. For a cylinder, it turns out that if you were to unravel this like the label on a can, the shape that you would get unfurled would be a rectangle. Right, for a cylinder. All right. If the idea of a volume is basically this, that it is, a volume is equal to an area times a third dimension, then notice in the volume formula for a cylinder, there's the area formula for a circle, pi times r squared. And again, just times how tall it is. Okay. All right. In that instance, you're just considering this as being one stack of pancakes, taller and taller. Once you figure out what the bottom is, area, you just multiply by the height dimension. Right. Area of the circle is, because the circle is the bottom, height is how many pancakes there are. Right. Down here, when you get to surface area, you see there is a 2 in front of the area of a circle, because there's a bottom area that is a circle, and there's a top area that's a circle. Right. This other portion of it here is to account for this rectangle that would occur if you were to unravel the side, flatten it out. Right. Why 2 pi r? Because 2 pi r is circumference. And the height dimension is basically like a width and a length. Okay. From here to here would essentially be the circumference. What we would regard as a length if we were thinking about it as a rectangle, right? The height would be equal to a width. Now it turns out when you have a cone, it's very similar, right? Here again, if you train your eye in the middle, there's the area formula, pi r squared. And there's the third dimension is the height, right? But when it comes to the volume of a cone, there's a 1/3 tucked into it. Because it turns out that the volume of a cone is 1/3 the volume of a cylinder. All right. Now as for the surface area, this is more complicated and I'm not doing it any justice, but you can see right away why, if you calculate the area, there's only one base, right? There's the area of a circle again, right? This, although I'm speculating right off the top of my head, comes from basically unraveling this label. If you notice that there's a radius dimension in here, I'm going to highlight this ever so slightly. There is what appears to be a right triangle from the dead center of this circle to the edge of the circle, right? And that would normally be labeled R, right? And then there's the height dimension, which would be from here to here, right? If you think about it like a standard right triangle and you consider the Pythagorean theorem, I would bet that this is based upon the Pythagorean theorem, but instead of calling it A and B potentially, the labels have been changed to R and to H, right? Why so? To figure out what this side would be. This much would be a hypotenuse in the context of a right triangle. Right, but if you were to unravel a cone, right, you're going to see sort of a circular shape. I don't know if it's exactly like this or like this, more like Pac-Man. I forget offhand. I think it would be something like that. Well, this would make sense. A half a circle, a semicircle. One of those dimensions, the hypotenuse dimension, has to be either a diameter, as in the case of a whole circle, or a radius. I forget offhand. I'm interested now, I can't help it. All right. And then there's this extra portion here, pi times r, which you notice is not quite a circumference. You know, if a circumference is 2 pi r, it's absence of that extra feature, the 2. Right? So that would have to be one of these other dimensions. All right. The bottom line is that the surface that wraps all the way around the edge is what this is derived from. Right? The area that would be this. I'm just forgetting offhand what the actual shape is. Right? If it's a semicircle, which would make sense, you know, it's not quite the whole circle, or if it's more like a Pac-Man shape. I gotta think about it. All right. Anyhow, a sphere and a pyramid are the let's 2, 3 more down here. let's start with the pyramid. It turns out again that there's this 1/3 in the formula, right? 1/3, the volume of a pyramid is 1/3 the volume of a cube. Right. The reason a lot of times they bring up the subject of oblique pyramids is because you can actually, like I had done this once years ago when I was teaching middle school. You could fold together from a flat pattern a Yang-Ma oblique style pyramid, right? Make 3 of them and then fit them all together and they make a complete cube, right? That's the reason for the 1/3. Now in this instance there is a capital B here. Capital B means the area specifically of the base. And they use that to distinguish it, capital B, from lowercase b. That's the area here. Why to generalize? Because the bases, as you know, in the case of the pyramids, they could be triangular base, they could be square base, as you see this, or a hexagonal base, something approaching a cone. So beware of that. All right. Then there's the volume of a sphere and the surface area of the sphere. Let's start with this part. All right, pi r cubed. All right, that's pi r squared times an extra dimension. All right, that's the area of a circle. All right, times a 3rd dimension. All right. So this would make obviously a perimeter, a volume, because it's an area times an extra dimension, of course. But then there's this factor here of 4/3. I'm definitely not going to do that justice in the time that I get allocated to this. But there's a video, it's an awesome video that I linked in Canvas that describes basically the idea, how you can derive this, right? It's absolutely fascinating, and the person who made the animation is, a true genius and a generous soul too, to provide that information. And so I'm going to link that. If you could, just in a nutshell, if you can imagine an ordinary circle as being cut up into pi wedges. All right, and then in the 3rd dimension it would be sort of a pyramid shape, extending towards the center all the way around. That's the basis of this idea. A surface area, there's a similar video just underneath it as well. Here is the area of a circle once again, pi r squared times 4. I'm going to have that linked. It's actually already there if you'd like to look at it. Here's a prism. These are easy. Capital B once again, because the capital B is the area of the base. All right, so if you figure out that the base of this is a trapezoid in this particular case, think of it as trapezoidal pancakes. That's kind of a bizarre breakfast, I suppose, right? But that's exactly what it is. If the bottom layer is a trapezoid and you stack them into a height, right, giving it a 3rd dimension, that's what the volume of a prism would be. All right. Now over here, there's Euler's Polyhedron formula. All right, it's sideways, so let me just rotate this. It turns out Euler, who is famous for many things, including the mathematical constant E, noted that the difference and sum of these features of any polyhedron will always produce the number 2. Right? So if you calculate the number of vertices to your unique shape, right, subtract the number of edges that would have, and then add the number of faces, you're going to consistently get the number 2, which is cool, because that means that in theory, if you have 2 out of the 3 pieces of information algebraically, you could always figure out the missing one. Right? Just make sure that you have this formula on hand. All right. Now let's do some examples. And I'll put this back in the regular orientation here. And I'll go through these. Okay. These are pretty straightforward. All right, you're going to be using the formulas unique to each of these shapes. Now, for those that have a circle in them, what I would encourage you to do is to, as I said yesterday, try to hold on to, hold off rounding until dead last step. All right, now, because pi happens to be an irrational number, it would seem that you would have to, do that intermittently, but you don't want to do that. You want to avoid it. If you incorporate pi, rig up the sequence that you are going to enter into your calculator so that you do pi last or as close to last as possible. All right. In this case, what you're asked to do is to round your answer at the end, not intermittently, to the nearest hundredths. All right. They want the volume and the surface area of each. All right. Let's see. What you would get from this volume is 100 feet square. Cubed, rather, because it's feet times feet times feet. 10 times 2 is 20, 20 times 5 is 100. The surface area, were you to calculate all of them, should be 160 feet squared. This is an area. All right. The volume of the cylinder, given these dimensions, let's do this one maybe. I want to give you just like 2 of them at least. And I'm trying to decide which one would be most appropriate. Let's see. My books fell over. Let's look at this cylinder problem first. I don't have a lot of space, unfortunately, so what I'm going to do is I'm hoping that it will be okay if I write this in red, just to separate it out from here. The volume of a cylinder, all right, remember, is the area of a circle times the height, all right? And there's naturally the pi symbol in it. Again, don't use 3.14, right? Use your calculator or something that is a scientific calculator that would have a pi button. All right, and only round after you've done all of the operations. All right. So, what is the radius here? As you can see that it would be 3, and the height dimension would be 7. Right. If this is just multiplication and this is an exponent of 2, which is an amped up version of multiplication, exponents is more important, then your focus would be to square this before you multiply anything else. That makes it 9. 9 times 7 would be 63. And basically what you want to enter is 63 times pi, right, into your calculator. I'm going to put this down. So you press 63 times, and then that, again, provided you have an appropriate calculator, you have a pi button for a scientific calculator, naturally. Enter that last Right? You'll have a very high degree of precision, and this is the figure that you get, right? 197 point something. So if you end up with 197.920, and you're asked to round to the nearest hundredths place, the hundredths place is where this 2 is. Right? So approximately 197.92. If the unit is consistently inches, it's inches cubed for volume. Right? As for the surface area, the surface area formula is the area of the two bases. Let's see, 2 pi r squared. That's the two areas of the bases, plus the unraveled label, if you will. So it would be a circumference for the length dimension, 2 pi r, and a height dimension would be standing in place of the width. Okay, so this is a little bit tricky because you have pi in two places. So what you could do if you wanted to be crafty is you can factor out the similar features. You really don't have to do this, and you could get away probably with rounding intermittently, but I wouldn't. I would try to set as good example for you as I possibly can. So what I'm going to do is I'm going to rewrite this so that I only have to press pi one time. All right. So if you think about this in a factored form, remember when you factor something, you're ripping out the common feature, right? Both of these terms, separated by a plus here, have a 2 in common, right? Both of these terms have pi in common, right? They also technically have an r in common, right? I'm going to maybe leave that alone because it isn't necessary to have to mess with it. All right, I just want to make sure that the pi is where it needs to be. In fact, I could, if I really wanted to, I could leave the 2 in there, but I'm going to leave r squared in here for now because I can get away with doing that. I could again put the r on the outside, but I don't want to. And r times h. Okay. So if this is factored, and there are now these parentheses here. Right. I have a 3 for the radius, which is really a 9, and a 3 for the radius times the height dimension, which is 7, which is really 21. And 9 plus 21 is 30. That means that what I would have to type into my calculator is basically 30 times 2, which is 60, times pi, right? And I'm going to hit that last. Pardon me, 60 times pi. So 60, got it cleared. Good. And you see that you get 188.4. Looks like a 9.5. Yep. Okay. So if this is 188.495, it's about 188 point, the hundredths place is where this 9 is sitting. Based upon 5 being adjacent, you would round up, but because it would round up to 10, that encroaches upon the next place, which would be 50. And if the units are in inches, this is the surface area, so it's inches squared. So you should get 188.50 if you keep the appropriate number of digits. Okay. All right. that's the basic idea, all right? Make sure that you try to rig it so that you don't have to round intermittently. If you do, you'll get something, as provided you follow the order of operations correctly, you'll get the correct answer, or something, you know, within a degree of accuracy, but it won't be as good. You know, this is an estimate anyway, pardon me, a rounded answer. So it's never going to be exact because of the irrational number pi, right? Imagine having to do that twice, though, as you would in the case of the surface area. All right. Now, just to be fair, the volume here of this cone, you should get about 65.97 inches cubed, and the surface area, it died. Come on. The surface area, sorry if that's hard to see here, 65.97 is the volume, about 100.05 inches cubed. Inches squared, which is an area sum. So 65.97, 100.05. All right, the volume here of the sphere is about equal to 904.78 inches cubed, and the surface area is 452.39 inches squared. Okay. All right. 904.78, 452.39. I want to see something really quick if I can. Oh, I don't have any cone-shaped things. I'm going to do an experiment privately later, and then I'll tell you what happens. This is bothering me that I didn't finish this one earlier. I believe when you unravel this, I've forgotten now, what you end up with is a semicircle. All right. It's just that it's been twisted, you know. All right. And that, if based upon whatever the shape is, that would decide why you have, you know, the other portions of the formula for the surface area of a cone. So pi r squared plus this times r squared plus h squared. Not to belabor the point, but I don't like to leave something if I can avoid it. All right. That is the area of a circle, because that's the bottom, and this would be the area of the label, for lack of a better word, unraveled. Just this much of it is like a hypotenuse. So think Pythagorean theorem. This other half of it has something to do with this, right? This predicts that actually, right? Because if a circumference is 2 pi r would just be that much. That my guess, without performing the experiment is that this is half of a circle. Right? Okay. What I want to do later, and I think I'll do that for fun, is I'm going to basically make a cone out of paper and then make sure that it has a completely flat bottom rather than what you see here. It looks like a terrible hat. All right, and then unravel it and see if in fact it is a semicircle. I believe it is. All right. That's my educated guess. Okay. Whether I'm right or I'm wrong, that's my guess for the time being. All right, now moving on. This is a little bit more interesting. All right, Robin needs to replace the sand in her rectangular sand volleyball court. All right, the court is 30 feet wide, 60 feet long, and notice that they changed the unit here. All right, and a uniform depth of 18 inches. And of course, there is a conversion factor of some persuasion written in here. Sand sells for $27 per cubic yard. So here's a conversion factor just to keep on hand, what we will translate into conversion factor. All right, $27 is equal to, it's really per, but we're going to write like this for now, a cubic yard without using the word a or the number 1. So a yard cubed, 1. Okay. 27 is that. All right, which means in the style of a ratio, you could either write it like this. In this phraseology of it, phrasing of it, 27 per, that would be $27 per would be the line, and then a yard cubed is under here, 1. All right, if you have it switched around, this is not really translating it the way it's written, but it would be correct if you needed it to convert that way. All right, now, there's two parts to this. How many cubic yards of sand does Robin need? All right, you'd have to find the volume of the volleyball court first, right? That's a subtle way of asking what's the volume. All right, identify the type of shape it would be. It would seem to be a rectangular solid, and in which case the volume of a rectangular solid is the length times the width times the height. All right, so 60 times 30, and then you can't use 18 here. You'd have to translate that to the same unit. You could make these all the same unit, but what's going to be even more of a nuisance later is that when we try to figure out cost here, we have to do it in terms of yards. So what you might do, and I'll put that here, is acknowledge that there's going to be double trouble here. This is feet, feet, and inches, and none of them are yards. All right. So there's lots of different ways you can do this. You can convert that to feet first, just to make this consistent, and then convert feet to cubic yards after the fact. That might be the easiest way to go about it. Or you can convert that to an amount of yards, you can convert that to an amount of yards, you can convert that to an amount of yards, and then the answer will be in cubic yards. Right? I think just judging purely by the relationships of these numbers to the relationship between feet and yards firstly and inches and yards, you might get away with doing all the converting first. So let me remind you, if you've forgotten, right? There are 36 inches in 1 yard, and simultaneously there are 3 feet in 1 yard. I'm well acquainted with the imperial system, as you can see, right? So you would perform a little conversion here, right? A conversion factor that would cancel inches would be this one. A conversion factor that would cancel feet would be oriented like this. 3 feet is 1 yard. So, let's see. If this is what you're given, 18 inches, and I want to convert that to yards, I would multiply by this conversion factor. 1 yard is 1 over 36. Right? And the effect would be that this cancels this. Right? And it would be 18 over 36, since that's 18 over 1. And that would be a half a yard. So this 18 inches is a half a yard. This 60 feet is what's given here. 60 times 1 yard over 3 feet, that's feet, would cancel that, and then you'd end up with 60 divided by 3, essentially, which is 20, right? So this 60 feet would be 20 yards. Right. And similarly, if you have this 30 given to you here, 30 feet times 1 yard is 3 feet. When you cancel, you end up with 30 divided by 3, which is 10. So what numbers are you really going to multiply? 20 times 10 times half as much. Right. 20 times 10 is 200. What's half of 100? 100 yards cubed. Right, would be this sandbox, essentially, in yards, cubic yards. Okay. Now, we can introduce the conversion factor that's appropriate here. If we multiply the number of yards, 100 cubic yards that is, times this specific conversion factor, not the one that is adjacent, because although it is theoretically possible, it's not practical in this case. This is what would happen. Yards cubed, 1 times 1 is superfluous. 100 times 27 is $2,700. That's what it should cost. $2,700 will be the cost of the sand in theory. Example 4 is similar. This is the types of problems, and the reason I'm spending more time with them is these are the types of problems exactly that you would see in Canvas, pardon me, in my lab. Okay. This, they don't give you much of a picture, so you can illustrate. The Camden College Athletic Hall of Fame building features a statue of a large volleyball. Somebody likes volleyball, whoever wrote these problems. All right. So, here's a volleyball, spherical shape, yay, on a pedestal. Okay. Hopefully that's not too faint. It doesn't really help it much, does it? Oh, green, why do you have to suck so bad? Really press it. That's a volleyball, I swear. Volley! Okay. The volleyball and is in need of paint. Alright. The volleyball has a diameter of 8.5 feet. So across the inside center of this is 8.5 feet. Let's see. Determine the surface area. Why? Because you would need to know a surface area in order to paint something. Alright. The surface area of a sphere is 4 times pi times r squared. Again, the derivation of this is quite clever. Alright. And I want to, as I mentioned, I'm going to link that video. It's really great animation. Alright. As to how this was derived. Also the volume of a sphere. So, we can calculate the surface area immediately. Let's do that. I would rig it again because you notice that there's pi in here. Like so. Alright. Push the stuff that you're going to type, you know, first into the front of this from the left. The radius would be 8.5 squared, right, since it's 8.5 feet. All right. You would have to square 8.5 times 8.5. So 4, do this. 8.5 squared times 4 times pi is the sequence that I would type. Okay. So 8.5 squared times 4 times pi. Right? You would see something like that. Right? That's just making sure the calculator doesn't mess up the order of operations, okay? And here's pi at the end. And there's your calculation. Looks like 907 reading it backwards. Let's see. Oh, I'm a ding dong, alright? Because I put a diameter where there should be a radius. So, what is half of this? Alright? Half of 8 would be 4. Alright? Half of 5 would be 2.5. Alright? So 4.25, sorry. 4.25. 4.25. Okay. Very clumsy, Ziegler. Okay. 4.25 squared, sorry, because we should be appropriately using a radius, times 4 times pi. There you go. All right. 226.98. Leave that on your screen. All right. 226.9. 8, whatever it is. I'm just going to put little ellipses here to indicate there's something after it. All right, and it's an area in feet squared. If they ask you to round, and in this case they didn't really specify, all right, you could just round it to anything you like, but I would, just for the sake of saving all of the infinity in here, don't erase that from your screen. All right. If 1 quart of paint covers about 100 feet squared, 1 quart is 100 feet, essentially. That's goofy, right? But that's the conversion, right? How many quarts of paint will the college need to buy to paint the volleyball? We have an amount of paint that it translates to an area, and we have a surface area, which is an area. So what we will do is translate this into the appropriately oriented conversion factor ratio, which would look like so. All right. 1 quart on top will produce the answer in quarts. 100 feet squared on the bottom will cancel. So if you multiply this that is on your calculator screen by this conversion factor, all right, this would be the effect. All right. This would cancel, feet squared, and leave you with an answer in quarts. And since what ends up happening is that you have 226.9 whatever on top, and you have 100 on the bottom, the effect is that the decimal is just going to move over twice. Just not a lot of paint, really. Number of quarts, it would be 2.2698, whatever it is, into infinity. All right. Now, again, it's not really specified how they want you to round, but in this case, you have to be logical. All right. Can you buy a fraction of a quart of paint? Usually, no, right? So even though it would be regarded as piss poor rounding, all right, to round this up to 3, you'd have no choice in real life because they're not going to let you sell you a fraction of a quart, you know? At least not really, right? Not a paint, you know? So badly rounded on purpose, you'd have to have about 3 quarts of paint. Okay? Capitalism in real life, consumerism, I should say, all right, makes you round badly for the sake of profit, right? Maybe the world is less rigid than me. For example 4, you have these 3 silos. All right, Gordon has 3 silos on his farm. The silos are each in the shape of a right circular cylinder. Those are the bases, if you will. One silo has a 12-foot diameter. One has and is 40 feet tall. The second silo has a 14-foot diameter and is 50 feet tall, and the third is 18 by 60. All right. Okay. So what they're asking, what is the total volume, capacity is synonymous, of all 3 silos? You would have to end up adding, essentially, volume of this, and this, and this, right, to get the total volume. All right. You take into consideration the shape that you have. All right. The volume of each one of these is going to be pi times radius times height, radius squared times height, but you will substitute different values, right? Bear in mind, all right, you're going to get pi in here, and pi in here, and pi in here. So although you can get away with rounding this to a decimal 3.14, the more that you do that, the less exact this answer will be. So what might be strategic is, again, even if it's not anyone's intuition, to factor it, right? Factor out what is going to be consistently the same here, so that you don't have to multiply by pi several times. You can just multiply by pi once in factored form. Factor out pi to multiply pi only once. That's the idea. All right. So consistently, I'm going to put it in some of the dimensions so we could see. The radius is not going to be the same each time. they're telling you again diameter. Don't do the dodo mistake I made earlier, which is I used the diameter when I should have used the radius. Half of 12 would be a radius equal to 6, right? Half of 14 would be a radius of 7, right? And half of 18 would be 9, right? Check the units, they're all feet, so that's fine. 6 would be here, and 40 would be here. 7 would be here, and 50 would be here. And 9 would be here, and 60 would be here. Okay. You could perform the arithmetic a little bit, but remember, hold off on translating pi to a decimal. You would have to square, so this would be 36 times 40. Times pi. And this would be 49 times 50 times pi. And this would be 81 times 60 times pi. Okay. Meanwhile, these are all onto a little universe unto themselves here. All right. Factor out pi. That's the common factor amongst all of these products. So, you could straighten that up, but I'm trying to do this appropriately. All right. Pi times the product of 36 times 40 plus 49 times 50 plus 81 times 60. That's pi extracted from each of these. All right. You might be able to get away with doing it like this now and to this exactly. Okay. Just as long as you incorporate a parentheses. You could write 36 times 40 plus that, but do be careful. At least in these instances, when you multiply these, if you choose to do those separately, you're only going to get a regular number, all right? That isn't even a decimal in these cases. All right, so let's see what I can get away with. All right, pi times 36 times 40 plus 49 times 50 plus 81 times 60. Now let's see. I'll go back here. I did press pi in the front here, which is fine, again, as long as I isolate it. So I'm hoping that my calculator knows that you must do all multiplications before you add, but we'll prove or disprove whether it knows the order of operations to that degree. 36 times 40, 49 times 50, and 81 times 90. And I close the parentheses. I'll see. All right. What figure is that? 27,488.94 approximately. So yes, it is correct. All right. The total volume is this. 27,488.935, whatever it is. And the unit would be feet cubed. Right? Did they specify it around in any way? No, but and I would hold off on rounding just yet. If they told you to round to the hundredths place, then it would be 9.4. Right. Now, if Gordon fills all three of his silos and then feeds his cattle 150 cubic feet of silage per day, in how many days will all three silos be empty? All right. Now notice what you have here, another conversion factor. This is feed, 150 cubic feet of feed, right, per day. That's like saying this. is equal to 1 day's worth of food. You could rig this in the style of a ratio so that there is a cancellation effect of the volume unit, cubic feet. And that will tell you how long it will be until this is empty. All right, if this is in fact the total. So this figure here multiplied by the conversion factor in this orientation, 1 day on top, 150 feet cubed on the bottom. Right? Although I'm sorry that these aren't stretched nicely. Right? This being on the bottom and this being on the top tier for 120, pardon me, for 27,000, such and such. All right, we'll cancel the volume unit and leave you with the day unit. Right? So essentially what that means is that you're going to have this figure that's on your calculator divided by 150. So without having to erase anything, trying to be strategic here, divide by 150, see what you get. 183.25. 183.259 days, which again, you'll have to round in this case just to be intuitive. When should a person, buy food, after you run out or just before, right? This would be appropriate rounding anyhow, right? Not like before when you're overestimating on purpose, all right? But you would say reasonably, here's the ones place where that would be whole days. Based upon a 2 here, you would simply round this to 183 days. Okay? Next. Let's look at Euler's Polyhedron formula. I'll erase some of the gobbledygook here. Okay. We're going to incorporate Euler's Polyhedron formula, taking into consideration the number of corners, vertices, edges, what we would think of as sides in 2 dimension, and faces, what we would call surfaces in 2 dimension, and see if it equals 2. Let's see, a certain polyhedron of 20 vertices, so this would be 20, and 12 faces. A certain polyhedron has 20 vertices and 12 faces. Determine the number of edges on the polyhedron. So if you have a 20 here and a 12 here, you have the majority of information, so you can play the game of algebra here. All right, but let's use an abbreviation. So minus e, shall we say, plus 12 equals 2. All right. Before you play the game of algebra, which is to move things over equals. Remember, compact together what you can via ordinary arithmetic. You have 20, you have 12. Add these together, and you end up with what? 32, right? 32 minus the amount of edges to answer the question equals 2. And you have a small table that you can construct. Drag 32 over here via subtraction, and you get this. Negative e equals negative 30 if negative e equals negative 30, then what would logically be true? Right? You could divide by negative 1 here, divide by negative 1 here, that would be appropriate. Right? And that will produce the desired result. Or you could reason to yourself, if it's negative is equal to a negative, then a positive would have to be equal to a positive. So 30 edges. Okay. Let's do 6. And nearing the end here. How are we on time? Not so bad. Let me scoot this up a wee bit here. Okay. This is an example where they give you the illustration, but it's a little bit small, unfortunately. You have to conclude a lot on your own, just based upon the shapes that you see here. All right, Frank's fish tank is in the shape of a hexagonal prism, meaning that it has a hexagonal top and bottom. It's connected laterally by what appears to be rectangles. I haven't seen too many slanted fish tanks. All right. Use the dimensions shown in the figure and the fact that 1 gallon, here's the conversion factor immediately, equals 231 inches cubed. Right. Firstly, determine the volume of a fish tank, right, in cubic inches, and then determine the volume of the fish tank in gallons, round your answer to the nearest gallon. All right. Let's see. All right. I could zero in on that. It's a bit tiny. That's a little bit easy to see, right? That's better. All right, let's calculate the volume of this. All right, the volume of a prism is the area of the base times the height. As it is with volumes, this is an area, right, times a third dimension. All right, the height dimension. So in this case, we're making a stack of pancakes, but let's call them waffles instead, because waffles a lot of times are hexagonal, right? Well, I'd like them to be. The little holes maybe are hexagonal. I don't know, but the outlying shape. It goes around. Yeah. But we're making a stack of hexagonal shaped waffles, shall we say. Right. So the area of the base, right, and the base happens to be a hexagon. Right. We don't have a formula for the area of a hexagon, but we can figure it out. We have, if you look at it in perspective, a trapezoid attached to a second trapezoid. And we have what appears to be enough information to figure out those necessary dimensions. Remember the formula: 2 trapezoids. The area formula of a trapezoid is 1/2 times the height times the first base plus the second base. Okay, so we can see the height dimension if you superimpose, if you sort of translated what appears to be the distance from here to here, the edge in the back to the middle, over to here, you can call this a height. So we have 8, right? 8 inches. All right. Now, as for the base 1 dimension and the base 2 dimension, base 1 is being explained here, translating backwards would be 8 as well. And the whole way across, translated down to here, would be 16. Okay, so we have the information that we can get this. Now, interestingly, that's just one trapezoid, right? That would be this much area, half of the hexagon in terms of an area. All right? It takes two trapezoids, it seems, to make one hexagon. There's a half in the formula, so if I just insert this next to it in sequence times 2, all right, I can maybe spare myself a little bit of work. All right? 2 times a half would cancel out the half and the 2 entirely. And leave you with 1 times 8 times the sum, which you really should do first. All right, 8 plus 16 is 24. Essentially, the outcome of this hexagon's area would be 24 times 8. So carry the 3. 2 times 8 is 16 plus 3 is 192. The area of one hexagon is 192 inches squared. Okay, so 192 for the area of the base times how many layers of waffle here? From here to here in perspective is the height, 24 of these. So 192 times 24, 8, 36, 7, 0, 4, 18, 3, 8, 10, 16. I'm estimating 4,608. Let me verify with my calculator here. Okay, 192 times 24 layers is 4,608. Good. All right. This volume, 4,608. And since it's inches squared times an additional dimension of inches, you get inches cubed. Save that information. Okay. Now, they also gave us a conversion factor. And the conversion factor is what? It is stated that 1 gallon equals 231 inches cubed. So if we translate this into either 1 gallon over 231 inches cubed, or if it is necessary, 231 inches cubed over 1 gallon, we could conclude how many gallons there are. Now, if we want to cancel out inches cubed, the volume, and be left with the number of gallons, then this is the appropriate orientation. So we would have 4,608 inches cubed. I'm just going to disguise this as a fraction by sticking a 1 under it, times this one, not that one. 1 gallon, I guess it's appropriate that it's blue, huh? We're talking about water here. This will produce the number of gallons. So this unit cancels this unit. 1 times that will give you 231 on the bottom. And 4,608 times 1 is 4,608 on top. So without having erased anything from your screen, divide by 231. And you get that. 19.9 looks like. So if this is 19.948, whatever it is, gallons of water, presumably, not acid. What a terrible fish tank aquarium owner you would be if you filled it with soda or something terrible. That's really sadistic, you know. They asked us to round this to the nearest gallon, so that would be an example of good rounding. Based upon knowing here, the nearest gallon is the whole one's place. So this is 20 gallons of water, is what it would be. Moving on. Okay. Back that off. Volumes of prisms. Let me get some water. I'll be right back. Okay. Determine the volume of the remaining solid after the cylinder, the triangular prism, and the square prism have been cut from the solid. All right. I like these types of problems because it's a very linear sort of way of thinking. All right. Start with the container that is the outermost container here. All right. What type of shape is that? The outermost container is a rectangular solid. And therefore you would use the volume is equal to a length times a width times a height incarnation of a volume formula, right? And this represents a whole, if you will, amount of something, a whole amount of space. So, from the whole amount of space, we are going to subtract a sum of three smaller volumes. All right. The volume of this rectangular solid, which has been called a square prism because of its bases, a triangular prism, and a cylinder. All right. And that will be the amount that is left over. Okay, so we would need to calculate the volume of the whole thing first. So let's do that because it's easy. It's 20 times 3 times 8. They're all the same units. Let's see. 20 times 3 is 60. 60 times 8 is 480. Okay. So this amount is 480 inches cubed to work with. Again, we're going to subtract a sum, but the sum is going to be of three independent volumes, which will be naturally added before they are subtracted. That's why I'm putting parentheses there. The volume of the cylinder is apparently 3 inches long, height it was, and a radius of 2. So, if this volume here, I'll put it blue, is the area of the base squared, r squared, times height, then it would be the radius of 2, which is 4, and the height of 3, which is 4 times 3 really, that's 12 times pi, all right? I'm going to save that here. Right, I'm writing my answers in terms of pi, again, just for the reason I keep mentioning, which is I don't want to round intermittently if I can help it. It isn't wrong, really, if you do that, and no one will get mad at you, but we would like to have the best answer, not just one that is really close to it. All right, when it comes to a triangle shape, you don't have to worry. This, for lack of a better color, all right, is a volume that is the area of the base again times the height. So if the base happens to be a triangle, remember the area of a triangle is base times height divided by 2 times the height dimension is 3. You know, that's all the height. So this base is 6. And the height here in respect of this triangular bottom is 4. Alright, so that would be 6 times 4, which would be 24. And 24 divided by 2 would be 12. And now times 3 for the height, that represents how long this is. Layers, basically, triangle pancakes. Times 3 would be 36, right? So this is 36. And it would technically be inches cubed again. This is inches cubed. This is inches cubed. And now you have this one, right? It's a rectangular solid, really. So it's 4 times, you can call it a square-shaped prism, and that's true, but a square-based prism, because it's 4 by 4 here. But it's 4 times 4 times 3 again. So this volume is length times the width times the height for all intents and purposes, so it's 4 times 4 times 3. And that is 16 times 3, which is 48. All right. So this is 48 inches cubed. All right. Now, again, just for the sake of not running into too much trouble, here's what I would do. All right. Combine the little that you can. Or you could factor, you technically can factor out too, because these are even, but let me do this. If you combine the little that you can on the inside of this parentheses, you can combine regular ordinary term of 36 to 48 and get 1484. And that means that you have 480 minus 2 pi plus 84. All right, inches cubed, inches cubed, inches cubed, but just to look at the numbers. Okay. You could, if you want to, factor out 2. Because these are both even. That's being twitty, but you know, it might be helpful too. So you'd have 480 minus 2 times pi plus 84. Okay. And if you want, you could switch the positions here and here. You could put 84 in front and pi after it. I think this is sufficiently factored and prepped to get as accurate an answer as you can. All right, so let's do this. All right. 480 minus 2 times, here's 480, the total, subtracting out what will be a product of 2 times pi plus 84. So there's pi plus 84. And I'm going to close the parentheses to be a good guy here. Alright, so if that's visible without the glare here. That looks sufficient. Alright, so 302. Alright. No, that's not quite right. Something is amiss. Oh, well. See what happens when you have sloppy handwriting? This isn't 2. It's a 12. Alright. Why? Alright. Because it was 2 squared is 4, and 4 times 3 is 12. It's 12 pi, not 2 pi, I'm sorry. Right. So, I could actually factor out a 12 here because of the relationship between 12 and 84. 12 times 7 is 84. Alright, so if I rip 12 away from pi, then I would put 12 on the outside, and I would put a 7 here. I'm sorry. Ding dong. Alright. 7. There you go. So, this may be overkill, but we like to have as accurate an answer as possible. Plus 7. So, typed correctly, factored correctly. 7 on the inside, 12 in the front here. Sorry, I don't have a fingertip on that one finger. I came over from the door years ago. Alright. Fun factoid about me. Let's focus here. There you go. 358.30. Alright. The volume left over should be this. 358. 300 trailing off into infinity inches cubed. Okay. So, did they ask us to round? No, they did not. If you did round it, all right, just say for the sake of consistency to the hundredths place, you know, about 358.30 inches cubed. Again, I would only do that rounding dead last, right? The reason why I seem to be overcomplicating things is because I know that if I use 3.14 here, it'll get me something close to that. But if you've ever wondered, geez, why does my answer not match the answer in the back of a book or whatever, it's because you rounded when you shouldn't have. You round last, and you have to rig your formulas so that you don't have to round intermittently. That's a good exercise. Okay. All right. Is this one? This is pretty straightforward. Very simple drawing of what appears to be a pyramid. Determine the volume of the pyramid as it is shown. This is a square-based pyramid, as you can see. Alright, so the volume of a pyramid is 1/3 the area of the base times the height. Alright, that is an area of a base. An area times the third dimension makes it a volume. 1/3 because it turns out that a pyramid's volume is 1/3 that of a cube. All right. Now, if the area of the base is 5 by 5, that would be 25. Right? If the height of this pyramid, assuming it's from this vertex point to the inside, there should be a little drawing like that usually, to make this a 90-degree angle to the point. So the dead center of the square base, right, that's times 6. If you have this 1/3 times 25 times 6, you could write it in the style of fractions by sticking ones here and here and here. All right, and then you don't really need to calculate it. People tend not to use fractions, but there's a fraction already in the formula, so take advantage where you can, right, and simplify where you can. There's a relationship between 3 and 6. They're both divisible by 3 because they're both made of that factor. That's the GCF, both. The greatest common factor of these two in consideration. So that would be a 1 here and a 2 here, which means that the volume should be, divide all the units on meters, 50 meters cubed. Okay. Now this one can get interesting because of the conversion factors that they're asking you about. Right. This is definitely where I would draw a picture even if there's not one given to you. It helps you get through it. All right, convert 1 cubic yard to so many cubic feet. Right, they didn't do that much at least. Right, here is a cubic yard. Right. 1 yard cubed. CU a lot of times they use as an abbreviation. If something, pardon me, is a cubic yard, that means that the dimension this way is 1, and this way is 1, and this way is 1. And it would be yards times yards times yards. All right. They already took the trouble of dividing it into Rubik's style here. But the individual relationships you would have to take into consideration, right? The individual parts. That's why I draw these myself, right? Because even if they didn't do that, you could always figure it out. All right. How many feet are in 1 yard? It's really 3, 3, 3. So instead of 1 times 1 times 1, it's 3 times 3 times 3, which means that this is 27 cubic feet. All right. Now you have a conversion factor that you've created. 1 cubic yard equals 27 cubic feet. And from that you can answer more complicated problems. So like, for example, they're asking, wow, if you have 8.9 cubic yards, how many cubic feet is that? Write what you're given. 8.9 yards cubed times the conversion factor we've just contrived. Rig it appropriately so that there's a cancellation effect. So if you want to get rid of cubic yards, that would have to be a denominator then. And if you want to end up with cubic feet, that would be a numerator more or less. So 27 over 1. Right? That means essentially that you're really just going to multiply 27 by 8.9. And in which case, what would you get? 240.3. Cubic feet. Okay. Then there's this one. What if you're given cubic feet and you're going to convert backward? Right. In a situation like that, you're just going to flip your conversion factor upside down. So if you have, I'm sorry, blocking it, 749.25 feet cubed, and you multiply by a conversion factor in this orientation, feet cubed down here for the sake of cancellation, yards cubed to satisfy the requirement here. In 1 cubic yard, there is still 27 cubic feet, of course, but the cross cancellation effect would cancel out cubic feet, and the effect is that you're going to have this figure divided by that figure. All right, why? Because there would be technically a 1 here, and times 1 on top is not going to change anything. Which means you have 749.25 divided by 27. Right. 749.25 divided by 27 produces 27.75. Yards cubed. Okay. All right. Lastly, Madeline, I believe that's how you pronounce. I had an aunt, Madeline. Madeline recently produced a home, right, with produced. Maybe she did. Madeline recently purchased a home with a rectangular swimming pool. Okay. You have a description of a rectangular swimming pool. Draw a rectangle to represent a swimming pool. Pool. Not billiard type. Alright, the pool is 30 feet by 15 feet. 30 feet, 15 feet. and it has uniform depth, all right, of 4.5. All right, so naturally this would be 4.5 feet. Yeah, sorry about the stuff behind it. Move that out of the way ever so slightly. Hopefully that's easy to see. Madeline lives in a cold climate, so she plans to, this is insane, plans to fill the pool with dirt, all right, to make a flower garden. That's a very nice flower garden, I gotta say. All right. And I guess if you live in a cold climate, maybe you're worried about the pool breaking if you don't take the water out of it. Although if it's in the earth, I wouldn't worry too much. Maybe it's above ground. That doesn't actually say. Anyhow, you imagine filling a pool with dirt. As you're an interesting person, Madeline. Dirt pool. There you go. I'm getting this makes me happy. This problem. Make a flower garden. Okay, how many cubic yards of dirt will Madeline have to purchase to fill the swimming pool? This bizarre individual is going to translates this to cubic yards. Okay, we already have a conversion factor from before because we bothered to do it. 1 cubic yard is equal to 27 cubic feet. Now that will be appropriate to use eventually because we have units of cubic feet here and they want the answer in cubic yards. So what is a pool but a rectangular solid? All right, the volume of this rectangular dirt pool is going to be 30 times 4.5 times 15. Which is what? All right. 30 times 4.5 times 15, which is 202.5 cubic feet. Something fell. What was it? I don't know. I thought I heard something. That's a decimal there, I swear. And now we're going to convert 202.5 to so many cubic yards using the conversion factor from the last problem. So I'll write this like so. If I want to cancel feet cubed, that makes the denominator. And yards cubed will be on top, 1 over 27. Essentially what you're going to have happen here is top times top, bottom times bottom would produce 202.5 divided by 27. And you get 75 yards cubed of dirt, right? Okay, and that's it. All right. Cool. All right. Sorry for the hiccups in between, but we are done with chapter 8. Right. So turn this off. For homework, if you're following along. Please do section 8.4 in my lab. And as I mentioned, all the videos that I've alluded to, there's 2 actually, will be available on Canvas. It's really fascinating. If you have the time, all right, how they came up with the formula for volume of a sphere, 4/3 times whoever they is, 4/3 times pi r cubed, and the surface area of a sphere is 4 times pi times r squared. Watch those, all right? The animations, it's something that you really, to do it any justice, you absolutely need animations, all right? And the person who prepared these 2, I can't really applaud them enough. It was such a nice thing to do, generous. All right, so take the time and maybe watch those, all right? I'm going to perform a little experiment with a cone later because I can't, it's itching. I can't stand not remembering if it was a semicircle or not, the base for that surface area problem for a cone, all right? Anyhow, I'll let you know. Have a good weekend and I'll see you again on Monday. Be careful out there.